Gents, this is Sunil, and we'll be talking about special relativity, a certain effect in special relativity, which is called the simultaneity of relativity. The relativity of simultaneity, not simultaneity of relativity. Okay, I do that a lot. I don't know why. So it's something interesting. It's like the Lorentz contraction or time dilation. It's how moving clocks slow down. That's time dilation. How moving rods shorten up. That is Lorentz contraction. And this is something. This is one effect where you can actually see the order of events changing. If you see something, if you see an event A happening after event B, you might change your frame and you'll see actually B happening before A. That thing happens. Yes, that is true. That thing happens, and it's physically possible. We can show that mathematically. But there's a certain class of events that can accommodate this kind of phenomenon. We're going to talk about that. So we'll be looking into what mathematical requirements need to be satisfied for this to happen, and what that means physically. So I want you to imagine two-dimensional space-time. You've got one dimension of space, one dimension of time. One-dimensional space is just like regular space, but you have got only one dimension. You can move forward and backward in space. Imagine you cannot move. Imagine you're in some kind of a tube. You can't move across or up and down. You can only move forward and backward. In fact, it's not that you cannot move. Imagine that there is no up and down. There is no across. There is only forward and backward in space and forward and backward in time. That's two-dimensional space-time. And in two-dimensional space-time, we have got our Lorentz transformation, which I'll write down in relativistic units. That is, I will write t instead of ct, and I'll write v instead of v by c. So there is no c in this system, as we'll see. That is my transformation. X prime is the x coordinate of a certain event as measured from a moving frame, moving with a velocity of positive v toward that of positive x, and t prime is the time coordinate of the event in the primed coordinate, and x and t are the corresponding coordinates in the non-moving frame. Gamma stands for, of course, everyone knows about gamma. Gamma stands for root over 1 by v square. I write v square because I have taken v as v by c, so v by c counts for v. So there's that. After this, we'll talk about Minkowski diagrams. This is one intuitive way. This is one quantitative way to make some sense out of relativity, to make some intuitive sense, if there is such thing as intuition in special relativity. This was developed by Hermann Minkowski in 1908. He was actually a mathematician, not a physicist. That's something interesting. So this is a typical Minkowski diagram, not a complete one. This is two-dimensional space-time. You've got space here, x-axis. You've got time here. For traditional reasons, we've got x on the horizontal axis and time on the vertical axis. We've got that transformation. Let us look at something. X-axis is actually all the points which have got the time coordinate 0. So if you want to find the x prime coordinate, let's make t prime coordinate 0. That would make t minus vx equaling 0, which is going to give us this line. I want you to work this out yourself. I won't be writing every little mathematical detail out here. And to find out the t prime coordinate, we'll make x prime equals 0, which gives us x minus vt equals 0, which gives us this line. Now what's curious is that these angles are going to be equal, and the tangent of these angles is indeed going to be v, that is velocity. Now v equals 0 means that the frame is not moving. V equals 1 means that the frame is moving with the speed of light, which is impossible. So yeah, v is in the units of the speed of light. 1 means speed of light, 0 means 0, and everything in between is just a fraction of that the speed makes with that, the speed of light. That's how we do it, and let's see how we find the space and time coordinates of events in these two frames. If I say there's an event A, then the space coordinate of A is, of course, this, that I drop a line parallel to the t-axis. On the x-axis, I call that xa, and to get the time coordinate, I draw a line parallel to the x-axis on the t-axis, and that's I'm telling all these details because we'll use this exact analogy on the other frame also to obtain the x prime and the t prime coordinate. So to get the x prime coordinate of A, will drop a line parallel to the t prime coordinate on the x prime line to get the x prime coordinate of the event A, and do the exact thing for, draw a parallel line parallel to x prime to get the t prime coordinate of A. I'll call that ta prime. So that's how we find out the space and time coordinates of events in a Minkowski diagram. This is a Minkowski diagram. Okay. Now we'll come to simultaneity. Simultaneity, how we define simultaneity geometrically is if two events, if you have this x and t, I won't draw the transform frames. If you have two events, say A and B, lying on a line which is parallel to your x-axis, meaning they have the same time coordinate, that is the geometrical definition of two simultaneous events. Now, two simultaneous events in x coordinate will be some events like A and B, which have the line between whom will be a parallel line to the x-axis. But to make these coordinates, to make these events simultaneous in my prime set of coordinates, I'm going to have B not here, but somewhere on this line. I hope that's clear. Because all the points on this line will have the same time coordinate in the prime frame of reference as that of A, because this line in itself is parallel to x prime coordinate. So had B been lying not here but here, I'd find B to be simultaneous with A in my prime set of coordinates, whereas A and B would have very different time coordinates in my unprimed frame of reference. So that's something. So that's basically the relativity of simultaneity. The events are some events which might appear simultaneous in a certain frame, won't appear simultaneous in some other frame. So what this was all about is we know what this x minus vt means. This means that if you have something, if you have an event in a certain frame which is static and you're moving towards it with a velocity v, the x coordinate that you measure as you're moving will decrease with that of time because you're approaching it. But we have got an exactly symmetrical situation with time also. We know what this gamma is for. This gamma is for time dilation. This is what is responsible. This is what is responsible for time dilation. This shortens and lengthens the time interval between two events. But what does this Vx really stand for? This Vx is called the phase term in the time. This is what is responsible for changing the order, for messing up the order of events as you change your reference frame. And we will discuss some of the repercussions of that in our physical world. So I'll make another diagram. I'll erase this diagram right now, and I'm going to show you something pretty interesting. So if you have, I'll make a bigger diagram actually. This requires a bigger diagram. I want you to forget about this right now. Nothing mathematical, just geometry. So if you have two events, say I'll make A out here and B, no, a little above, A in here and B there. Yeah, that works for me. It's apparent that A happens before B because A has a smaller time coordinate than B. Now say I transform my coordinates. I transform my frame of reference. I change my frame of reference and then I get a transform frame of coordinates. There was wrong use of terminology. That's not a straight line. Right. I need a line. So we go slope. I'll call it time coordinate. I'll call this t prime coordinate. Makes it a little clear. Sorry. Okay, so I'll measure my time coordinates of events A and B in my transformed frame of coordinates. I'll draw a line parallel to the x prime axis from A hitting the t prime axis right here, I'll call this ta prime, and I'll draw a line parallel to the x prime axis, cutting the time prime axis here, and I'll call this tb prime. Do you realize what just happened? I have got a lesser coordinate, I've got a lesser value for t prime b, and I've got a bigger value for t prime a, which means that b actually happens first in my moving frame, and a comes later. So a is someone shooting a bullet, Alice, and b is Bob taking a shot. And it would be a physical problem, it would be a conundrum, it would be a physical, I don't know, mess of things if the bullet was actually fired after taking the shot. That wouldn't be possible. So let's see why that wouldn't be possible. So the angle alpha, okay, so yes, I have already said that if you have a tilt more than that of theta, that is v, the lines of simultaneity would drop steeper like that, and that's the way you can have the time coordinate of b being less than the time coordinate of a, and a happening before b. So if my theta needs to be steeper than alpha, that would mean tan of theta is more than tan of alpha, which would mean what I'm writing right now, that is tan of theta being more than tan of alpha, and my alpha is nothing but delta t by delta x. Tan of theta is also v, so I could write del t by del x being less than tan theta was v, and for the sake of the world, v is also smaller than 1. That would mean del x by, okay, let's forget the v for some time, and we can only write a statement like del t by del x is smaller than 1. That works, that's mathematics. And from there we can write del x by del t more than 1. I'll write it clearer somewhere, or probably erase what I mean. I'll erase the transformations, that's not serving any purpose anymore. So there's that. Del x by del t, which also happens to be equal to u, becomes greater than 1, which is not possible. Nothing physical can travel with a speed that of more than light. That is more than that of light, which is 1 in our units. So we see that these two events, where this kind of a separation in space-time is called a space-like separation. This is when no physical signal can travel from out here to out there, because if it does, it needs to cover this much space in this much time, and that would require a speed that is more than 1, which is not possible. So if event A has to influence event B, some kind of physical signal needs to travel from A to B. It could be sound, it could be your mechanical waves, it could be our good old electromagnetic waves, light, microwave, radio wave, anything. Some physical signal needs to travel from A to B to affect B. But that signal would need to travel with a speed more than that of light. So these two events cannot be correlated physically. These two events were destined to happen the way they are, and they're not related. Yeah, I cannot find a better way to put it. That's the best I could do. So yeah, that's it. So these two, there could not have been a bullet faster than light, because that bullet, if it had to hit B, and it emanated from the gun of A, it would have to travel at the speed more than light. So there is no bullet in the world like that. So that's not right, what I said. These two events cannot be someone shooting a bullet and someone taking the shot. Those events which are related have to be time-like separated events, which will always have a slope more than that of 1. So we saw how events can change their order in time with depending on the perspective you're seeing it from. You change your frame and events can change their order in time, but only on one condition, that they be space-like separated. Space-like separated meaning they're not physically correlated. They're not cause and effect pairs. One event is not the effect or cause of one another. They have to be independent, completely physically independent events. They're destined to be occurring at those times. Only then can the order of events flip as you change your frame of reference. And we'll end with that truth, the nature of truth is in fact invariant. It defines our world. Even the relativity might seem to suggest that it won't be, but ultimately it does say that truth, the nature of truth, the fundamental physical laws are in fact invariant and not changeable. Thank you for watching the video.